Today, we are going to talk about transient analysis. And so a good starting point would probably be explaining what the heck that means. I'm going to call this specifically transient analysis of first order circuits. All right, so let's consider the following circuit where we have a practical current source. So we have some current IS connected in parallel to some resistance RS. And now we're going to have a switch. And this switch is going to open at a specific point in time. And this practical current R and an inductor L. Like so. Okay. So I'm going to define our quantity of interest here to be our inductor current IL as a function of time. And what we're going to do today is to figure out how we can mathematically model that inductor current based on our current level of circuits knowledge and what we understand is happening in the circuit, okay? So, let's look at what's going on at t is equal to 0 minus. So let me start by asking you guys, do you understand by what I mean t is equal to 0 minus? Anybody have a thought? The moment right before 0, which in this case is the moment right before the switch opens up. So effectively, from t is equal to negative infinity all the way up to 0 minus, this is a DC circuit, right? That switch is closed. And so we simply have that inductor, or excuse me, that current source IS in parallel with that resistor RS, in parallel with that resistor R, and in parallel with that inductor L. So if we drew our circuit model for this specific point in time, it would look something like this. We have IS, like I said, in parallel with RS, in parallel with R, and it's going to be in parallel with that inductor too. But since it's a DC circuit, what do we treat the inductor as? A short circuit or a section of wire, okay? So this wire right here represents our inductor, and we will have some inductor current, IL, that's valid at this specific point in time, t is equal to 0 minus, okay? Who can tell me what that current should be? Pardon? That is correct. The short circuit there means that the inductor does not exhibit any resistance whatsoever. It is being modeled. It's just the source current, exactly right. So all of the current provided by the source is going to wind up flowing through that inductor. None of it is going to branch off and flow through either of those resistors. So we could say that IL at 0 minus is equal to IS. what are the implications of that? The inductor has a constant amount of current flowing through it, which means the inductor is storing energy, right? If the current flowing through the inductor is non-zero, then energy is stored in the inductor, okay? So we have some fixed amount of energy that's being stored. Now, I'm going to come up here real quick, and I'm going to make a graph. Of our inductor current as a function of time. Here's IL of t, here's our time axis, and just for the sake of argument, let's say that this tick mark here represents that current IS. What we have just mathematically shown is that the inductor current has a constant value. It would help if I could draw a straight line. Having that value of IS all the way up until the moment that that switch opens up, okay? This portion of time here is what's called a DC steady state condition, okay? Because the circuit is behaving as a DC circuit. As soon as we open that switch up, we are no longer at DC steady state because a change has occurred in our system. That changing system is called the transient condition. So for the time after our switch opens up, we have our transient condition. All right, so let's look at how this guy behaves at exactly t is equal to 0 plus, using our current understanding of how inductors behave. All right. So at t is equal to 0 plus, this represents the moment immediately after that switch opened up. So we're going to replace the switch with an open circuit. So we're going to have our current source IS, in parallel with our resistor RS. And then over here, we have our resistor R in parallel with our inductor L. There will be some inductor current. I'm going to call it IL at t is equal to 0 plus. And that bottom line there is all connected, right? So this is what it looks like immediately after our switch has opened up. Now I want to be clear here. I cannot represent my inductor as a short circuit anymore because we no longer have a DC circuit. Now this looks like it's going to be a DC circuit, and we're absolutely going to perform DC circuit analysis on it to an extent. But because we have moved from that DC steady state into a transient condition, the inductor, we can't simply brush it away and say it's a wire anymore. It's now actually behaving like a specific circuit component, okay? But if you will recall our first equation for how an inductor behaves, V is equal to L di by dt. What was the consequence of what was the second statement that we made about that when we looked at that particular expression? Anybody have a thought? We talked two different things. The first one was, number one, to a DC circuit, an inductor looks like a short circuit. We found that out by looking at what happened when the current that flows through the inductor doesn't change. Benjamin.
Was the second statement that the current across the inductor can't change?
That is absolutely correct. The current flowing through the inductor cannot change abruptly. So what that means to us is that at t is equal to 0 plus, that inductor current has to stay at IS, or it has to stay at whatever value it had at t is equal to 0 minus. All right, so it's still IS. So if we go back to our graph, we know that at t is equal to 0, approaching it from the left and approaching it from the right, our current will have exactly a value of IS at t is equal to 0. But something very important is happening here, okay? When that switch opened up, that current source, IS, is no longer influencing the behavior of the inductor, right? So we know that there's some energy stored in the inductor because there was current flowing through it. And at this exact instant in time, there is current flowing through it. So there must be energy stored. So what's going to happen is that that inductor is going to transfer its energy to the resistor over time. And the resistor will convert that current into heat until a very, very long time down the road, all of the energy stored in the inductor is converted to heat. So what I mean by that is if we look at this circuit at t is equal to infinity, or really just a very long time after our switch has opened, what our circuit's going to look like is this. So we're going to have IS in parallel with that resistor RS, and then we're going to have R in parallel with a short circuit again, okay? Here's our current IL at infinity. And so again, this at infinity bit means after all of the energy stored by the inductor has been converted into heat by the resistor. So just using our simple DC circuit analysis techniques, what do you think our inductor current at IL at infinity is? 0 amps, right? If the inductor doesn't have any more energy stored, then the current flowing through it must be 0. So if we go back up to our graph, at some time infinity, we know that our current flowing through our inductor is 0 amps, and it's going to continue being 0 amps. So the question is, well, actually, let me go back one step real quick right here. So after t is equal to infinity, we have another DC steady state condition. Okay. So what we are trying to solve today is what the heck happens in between those two DC steady state conditions. So how does this circuit behave during the transient, right? And that, for better or worse, is going to involve some calculus. Let me know when I can start writing again and scroll down and all that jazz. Yes. The current flowing through an inductor cannot change abruptly. So we are talking at t is equal to 0 minus, the current has some value of IS. An instant in time later, it has to say the same thing because it cannot change super quickly, right? So that's why. That's a fantastic question. I'm going to burn that into your mind. Okay, we're going to talk about it a lot, over and over and over again. We're going to use that over and over and over. All right, so let's talk about what's going on in general for t greater than 0 plus. Okay, so I'm going to redraw my circuit. So for t greater than or equal to 0 plus. So this is the moment after the switch opened up, and then a little bit more. Okay. We have our current source, IS of t. We have our resistance, RS. We have our resistance, R. And sorry, that looks like a resistor, not an inductance. We have our inductance, L, like so. And everything is connected in this way, IL of t. We're trying to figure out, all right? Now, Kirchhoff's current law and Kirchhoff's voltage law have to be satisfied at all points in time, right? Because Kirchhoff's current law is the law of conservation of energy for circuits, and Kirchhoff's voltage law is the law, Kirchhoff's voltage law is the law of conservation of energy. Kirchhoff's current law is the law of conservation of charge for circuits. So what I'm going to do is I'm going to say that since there's some current flowing through my inductor, and it's not a DC current because changes are happening, so I could argue that it's probably not going to be constant, I would expect to see a voltage drop across my inductor. And similarly, I must see some voltage drop over my resistor VR as well, right? So what I can do is I can apply Kirchhoff's voltage law, and I can say that VR of t, sorry, plus VL of t must equal to 0 volts. Okay, anybody got any problems with that? Hopefully fairly straightforward. And I've assigned all my polarities in such a way to make that happen. There's current flowing through it, and ostensibly the current might change. Even if it doesn't change, I can still say that there's a voltage drop. It would just be 0. But I'm arguing that as our inductor transfers energy to the resistor, if the energy level or the amount of energy stored in the inductor decreases, the current flowing through the inductor must decrease as well. I'm ignoring any internal resistance of the inductance. I'm only concerning myself with the fact that the current flowing through the inductor is changing, which is going to give rise to some voltage drop across the inductor, based on the relationship V is equal to L di by dt. So if the current changes, a voltage will appear. Right? I can take this expression. I'm going to have to do it on a separate page because I'm running out of room here. And I can relate both of those voltage drops to that common inductor current flowing around in that little right-hand loop. Okay. So for instance, the voltage drop over the resistor, if we look up here, is just going to be the resistor value times that current IL, because the current is flowing into the positive polarity terminal of the resistor. So I can say that VR is simply R times IL of t. And using the current voltage relationship for the inductor, I can say that the voltage drop over the inductor, VL, is equal to L di by dt And because I'm simply applying Kirchhoff's voltage law around, have to be equal to 0. Anybody know what this is? Drew. This is a differential equation, but it's a very special type of differential equation. It is a linear, homogeneous, first order differential equation, okay? So for those of you who haven't had Math 245 yet, what we're about to do might not make a whole heck of a lot of sense, but I'm going to try to simplify it as much as we can. For those of you who have had Math 245, you're going to be bored for the next 3 to 5 minutes, okay? Our goal here is to figure out what type of function IL must be to satisfy this equation, okay? So I want IL to be a function where I can add the function and its derivative together with some scaling factors, and they combine together to be 0. Can anybody think of any functions where that would work? An exponential function, okay? That is the correct answer, but one that I hear pretty often is also sinusoids. Sinusoids will not work for this first order exponential function because when we take the derivative, we wind up introducing a 90-degree phase shift and all that kind of stuff. And I'll talk a lot more about that when we get to steady state sinusoidal analysis. So we're going to take an educated guess here, and we're going to guess that our current IL of t of the form AE to the ST amps, where A is just some constant value that we're going to have to figure out, and S is another constant value that we're going to have to figure out, okay? So if I plug my guess for how my current behaves into my equation, I wind up getting R times AE to the ST plus SL AE to the ST is equal to 0. There is a common factor of A, so I'm going to take that guy out, and I'm going to have R plus SL times A, and there's a common factor of E to the ST is equal to 0 as well. So under what conditions would this equation equal 0? Right? There's one that's very, very obvious. A is equal to 0. What A is equal to 0 represents is that there was never a voltage or current flowing through the system at all. So effectively, we never charged or discharged our capacitor. So that only works if IS happens to be 0. It's a trivial solution, okay? It doesn't really tell us any information about how this thing behaves, because effectively we're saying the whole system was off the entire time, right? So we got to get a little bit more creative than that, unfortunately. That exponential function, e to the st, can approach 0 if s is negative and we wait for a very long amount of time, but it will never exactly equal 0. So what we're going to do is we're going to use this guy right here, which is called the characteristic equation. And figure out a specific value of s that makes this equation go to 0. That s is what's called the natural frequency of our system. Okay. So what must the value of s be to make that bit there in the middle equal 0? Negative R over L. Yeah, just the middle part. So we can update our guess now. A e to the negative r over L. P. All right. So now we need to figure out what A is. This actually is pretty simple, okay? Since we're dealing with an inductor current, we know that the inductor current cannot change abruptly. So for t at 0, like if we evaluated this guy exactly at 0, we would have IL of 0 is equal to A times e to the 0, which is just A. So I'm going to replace A here with IL at 0. And this is how our inductor current will behave during the transient condition. It will exponentially decay. It will start off at the value it had at t is equal to 0 plus, and then it will gradually decay until it is effectively 0 at some long point or long time in the future. And the rate at which it decays is dependent on the value of that resistor R and the value of that inductor L. We derive this for a generic system, which means it is valid for any and every RL circuit that undergoes a change in the system. Okay, true for all of them. So for those of you who are less than enthused about calculus, congratulations. We don't have to do it anymore. We know what the answer is. Now we just make the circuit fit these parameters. That's it. All right. So I've brought one of my numerous circuit analysis textbooks, and we're going to work an example problem to illustrate the process for solving these first order circuits. Okay. So I've just picked a circuit that I like, and we're going to run with it. So let me do this in black. Let's say that we have the following circuit, where we have a 12-volt source, a switch that is opening at t is equal to 0, and then we have a 6 ohm resistor here, a 12 ohm resistor here, and a 2 Henry inductor here. And I want us to determine two quantities now. I'm going to be tricky with you. This inductor current, IL, as a function of time, and this resistor voltage, VR, as a function of time. Okay. Here is the steps that we should take when we are given in. We're developing these for a RL circuit, but they will work equally as well for an RC circuit, and that's literally what we're going to talk about next. Okay. Step 1. Analyze the circuit at t is equal to 0 minus. Okay. So At t is equal to 0 minus, is my switch open or closed? Closed, all right? At t is equal to 0 minus, this is a DC steady state condition, which means our inductor is going to behave as if it were a short circuit, all right? So the simple approximation of how this guy is going to behave, sorry, this should be a 12-volt source, not a current source. A 12-volt source in parallel with a 6-ohm resistor in parallel with a 12-ohm resistor. Here's my current IL at 0 minus. Here's my voltage VR at 0 minus. Now we're going to solve for these two quantities at t is equal to 0 minus, okay? How we solve for them is entirely up to us. So, any thoughts on how we might solve for either of these two quantities? All right. So, we can see by inspection that our voltage drop across our resistor at t is equal to 0 minus is 12 volts because there's a 12-volt source in parallel with that resistor. So hopefully that seems pretty straightforward. All right. How do we figure out what that inductor current is? Okay, so the voltage drop across the 12-ohm resistor is 12 volts. And since the current flowing through the 12-ohm resistor is the same as the current flowing through the inductor, we would have 12 volts over 12 ohms is equal to 1 amps. Anybody have any questions, comments, or concerns about that level of circuit analysis? Now we are going to analyze the circuit at t is equal to 0 plus. So we are going to have our 12-volt source and an open circuit because our switch is open now. We have our 6-ohm resistor over which a voltage drop VR at 0 plus appears. We have our 12-ohm resistor. And now we have an inductor down here, L, and we know for certain that this current IL at 0 plus is equal to 1 amp. The reason that we know that is because the current through an inductor cannot change abruptly. So whatever value the inductor current had at t is equal to 0 minus, it must have at t is equal to 0 plus, or we have violated the laws of physics. Okay, that's how much of a it must be this thing. All right. So I can say definitively IL at 0 plus is equal to 1 amp. So I'm about to do something here. You don't have to do it by any stretch of the imagination, but it helps me in my circuit analysis. Okay? The current that flows through the inductor at this very fixed point in time, t is equal to 0 plus, is constant. It does not matter what the voltage drop over the inductor is or anything like that. This inductor is going to have 1 amp's worth of current flowing through it, direction down. So at t is equal to 0 plus and at t is equal to 0 plus only, this inductor is behaving like an independent current source. It is forcing a fixed amount of current to flow through the circuit, regardless of the voltage drop over the inductor itself. So we can model this inductor as a 1 amp current source so that it has the same magnitude as the inductor current, and its direction is down because that's the direction that the inductor current flows. Okay. You can leave the inductor as an inductor and just understand that the inductor is feeding current to the rest of the circuit. But for most of us, probably having it look like a component we've seen before may be helpful. Okay. So with that in mind, what is the voltage drop over our resistor at t is equal to 0 plus? So what is the voltage drop over, what's VR? Right, that's what I'm looking for, VR, very specifically VR. Negative 6 volts, okay? Because the current makes this corner and starts flowing up into the negative polarity terminal, so the voltage is going to be negative. And 1 amp times 6 ohms looks like 6 volts. So we have negative 6 volts. Now, I'm going to do this third step here with the understanding that it's actually not going to give us any information, but when we talk about what's called the total response, this will be important, okay? So step 3 will be to analyze the circuit at t is equal to infinity. Okay. So what's our expectation here? Any thoughts? The inductor current will be at 0 and the resistor voltage will be at 0. Whenever we're taking the source out of the system, that will always be the case. But I'm just trying to get you guys into the habit of this, because when we do what we're going to do on, if today's Wednesday, Friday, we'll have to introduce this step anyway, and it will actually give us something. So if we analyze the circuit at t is equal to infinity, actually, at t is equal to infinity, recall that we are at DC steady state conditions again, which means that our inductor is now behaving as if it were a short circuit. So here is our current, IL at infinity. Here's our voltage drop, VR at infinity. And by inspection, we can see that both of these quantities are 0. So I 100% understand if you don't actually do this step. All right. Yes, ma'am. Sure. So that current of 1 amps, let me draw its path, right? So we have a current of 1 amps that's flowing through the inductor. It hits this corner, and then it has a chance to either flow to the left. Some portion of it can flow to the left, and some portion of it can flow up, right? The left-hand path contains an open circuit, which means none of the current can branch off and flow to the left. So all of it must flow up into that resistor. So we have 1 amp of current flowing into the negative polarity terminal of a 6 ohm resistor, which is how we get negative 6 volts. Okay. All right. I don't understand the question. All right. Well, then let's move along. All right, so the next thing that we are going to do, okay, so we know how the circuit behaves kind of at its endpoints, right? So we know how it behaves at the beginning of the transient condition, and we know how it behaves at the end of the transient condition. And we have mathematically shown that there's going to be an exponential decay, right? Based on the resistor value that the inductance sees and the inductance itself, okay? So what we need to do is figure out now, in this case, what resistor value the inductor sees and what inductor value that equivalent resistance sees, okay? So step 4 is going to be determine LEQ and REQ, and I'm going to write this during the transient condition, and I'm going to underline that during the transient condition part in red, so that I'm drawing your attention to that very specific statement, okay? Because we're analyzing this circuit during the transient condition. So that means we're looking at how it behaves for t greater than 0 plus, okay? So to analyze this, let's start with LEQ. Anybody have any thoughts on what our equivalent inductance might be for this circuit? Let me scroll up here. 2 Henrys. I feel like that's a pretty darn reasonable guess considering it's the only inductor in the circuit, okay? So I feel very strongly that we can start there with some degree of authority. During the transient condition is going to be 2 Henrys because it's the only inductor in this circuit during the transient condition. Are we okay with that? The resistance is a little bit harder, okay? But we have the skills and knowledge to determine it, okay? So what we are trying to do here is to really determine the Thevenin equivalent resistance seen by the inductor, okay? So during the transient condition, our circuit looks like this. Right? This is what it looks like during the transient condition because we're looking at it after the switch is opened up. All right. We are finding the Thevenin equivalent resistance. So when we're finding the Thevenin equivalent resistance, what kind of network do we absolutely have to have? A dead network. How do we make this a dead network? Turn off the voltage source. So we're going to replace that 12-volt source with a short circuit. All right, step 1 is complete. Now, as I mentioned a moment ago, we are finding the equivalent resistance, the Thevenin equivalent resistance, from the perspective of the inductor. So what do we need to do? Take the inductor out and look in through its open circuited terminals. So I'm going to pluck this inductor out. And we're going to look in. And this is what REQ is. Because we're trying to see what resistance the inductance sees. So that's going to be the Thevenin equivalent. That's our technique that we're using. That's a technique that we will always use to find the equivalent resistance seen by another component. So, what is the equivalent resistance or Thevenin resistance seen by this inductor? All right, so you're saying that it sees the 12 ohm resistor in series with a 6 ohm resistor, right? Okay, I agree with that. Step 5 will simply be plug our information into our generic equation. Then misspelling generic, excuse me. So this is the first time that you're going to see our generic equation, but we actually, this is what we derived a little while ago, okay? So my generic equation, I'm going to say that y of t, which is just a quantity that I'm interested in. So it could represent inductor voltage, inductor current, resistor voltage, resistor current, and it'll also work for capacitors when we get to that too, okay? There's going to be a piecewise function. It's going to be y at t is equal to 0 minus for all t less than 0 minus. And it's going to be y at t is equal to 0 plus times e to the negative r over L t for t greater than or equal to 0 plus, right? So we derived that exponential bit earlier, and we showed that that y at 0 plus is just the initial condition on the system, okay? So it's nothing different than what we did at the beginning of the class, but I'm making it apply more generically. And the reason I'm doing that is that we applied that equation, or we derived that equation specifically for the inductor current only. But it has to apply to every other component in the system, okay? So let's look at just the inductor current for right now. IL as a function of time will be the inductor current at t is equal to 0 minus. So that was 1 amp for t less than 0 minus. And it will be the inductor current at t is equal to 0 plus, which is 1 amp e to the minus r, which is 18 over L, which was 2. So e to the minus 18 over 2t amps for t greater than or equal to 0 plus. And I should make this look more like a 1. Okay, that's a fantastic question. The inductor current, this needs to be a continuous function, right? And so what I mean by that is the inductor current cannot change abruptly, okay? So if it were positive 1 amps at t is equal to 0 minus, it has to be positive 1 amps at t is equal to 0 plus. That is not true for the inductor voltage or the resistor current or the resistor voltage, okay? And we'll see that in a moment. So I want to take what we have right here. We're not going to use our generic expression. I want us to determine how the resistor voltage absolutely has to behave, because we know that the inductor current behaves like this, right? We've mathematically derived that it has to behave like this in order to satisfy our system equations, right? So let's scroll up here. Let's look at what's going on, okay? So we know that our resistor voltage, V of t, will have some value when t is less than 0, and it will have some different value when t is greater than or equal. So let's see, 0 minus here, and I'll put 0 plus here, okay? Our resistor value, or excuse me, our voltage drop across our resistor for t is less than 0 minus is going to be what? Don't we literally have it written down right here? Right? It was 12 volts. It's going to continue to be 12 volts because it was just connected in parallel to a 12 volt source. Now, at t greater than 0 plus, what's happening? All of this resistor current, or excuse me, inductor current here that is well defined is going to wind up flowing into the negative polarity terminal of that resistor. So we're going to have 1 e to the negative 9t flowing into the negative polarity terminal, right? Which is going to give us a voltage of negative 6 e to the minus 9t volts. We got that by using Ohm's law. Current flowing into the negative polarity terminal, V is equal to negative I times R. Nothing remotely new. Okay. So effectively, what I am saying here is that if the current flowing through the inductor decays exponentially, Kirchhoff's current law tells us that the current flowing through the resistors that are connected to the inductor has to also decay exponentially because Kirchhoff's current law needs to be satisfied. And then Ohm's law tells us that the voltage drop across the resistor will also decay exponentially. And Kirchhoff's voltage law then tells us that the voltage drop over the inductor will decay exponentially. So what we're going to see in these transient analysis problems is that if one thing behaves with this exponential decay, everything behaves with this exponential decay in order to satisfy Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. So this is our result that we got by applying rational circuit analysis techniques like by Kirchhoff's current law and then Ohm's law. Okay. Now, let's see what happens if we throw the numbers that we've gotten into this generic expression. Jess. Okay, let me go back up here and explain it one more time. This inductor current we have found to be 1 e to the negative 9t amps. That current is flowing into the negative polarity terminal of the 6 ohm resistor. And Ohm's law tells us then that the voltage drop over the resistor needs to be negative 6 e to the negative 9t volts. That makes sense. All right. Now let's go back down here and look at our generic expression. VR of t. So what was the voltage drop over the resistor at t is equal to 0 minus? What was the voltage drop over the resistor at t is equal to 0 plus? No, at 0 plus, it was just negative 6 volts, right? Look at what we did. At 0 plus, we just have negative 6 volts. Okay, so what I'm trying to impress upon you guys is that we don't actually have to do circuit analysis to figure out how all these dang things behave. If we know how they behave at these critical points of 0 plus, 0 minus, and infinity, we can literally just plug that into our generic expression and we will be 100% correct these voltages and currents are, okay? So at 0 plus, we have negative 6 volts, and then we multiply that by e to the minus r over L. So sorry, that should have been a negative sign there. Negative 18 over 2, which is 9t volts. So doing no circuit analysis whatsoever gives us the exact same results as doing the circuit analysis. So I would argue, don't do the circuit analysis, right? It's not necessary, it's redundant. I'm telling you guys, follow these little steps, plug crap into a generic equation, and you will get the answer correct every time. That's an engineer's wet dream, okay? That's what you guys are here for, is, oh my gosh, I have an equation that works for everything. It's right here. All right, let's do another problem. I got time, yeah. So let's say that we have a 2 kilo ohm resistor. Six millihenry inductor. Five kilo ohm resistor. And then trying to think how to draw this well. Three amp source connected to a switch. Here's T is equal to 0. Here is just a simple short circuit. Like this, okay? So what's happening here, actually, let me put A in a different place. Here's A, here's B. So the switch is closed at position A at T is equal to 0 minus, and at T is equal to 0 plus, it then closes to position B. Okay. Analyze the circuit at T is equal to 0 minus. So at T is equal to 0 minus, our switch is closed at position A. And so, oh, sorry, let's talk about what we want to find here. Here's IL of T, and let's do this voltage VR of T. Okay. So we analyze the circuit at T is equal to 0 minus. And so that is going to look like 2 kilo ohm resistor. In series with a 6 millihenry inductor, or excuse me, in parallel with a 6 millihenry inductor. And actually, I've made a simple mistake there, but I'll talk about it in just a second. 5 kilo ohm resistor goes here. 3 amp source goes here. The mistake that I've made is that we're at DC steady state, so my inductor should be represented by a short circuit. Here's our inductor current, IL at 0 minus. Bless you. Here's my resistor voltage, VR at 0 minus. Any thoughts on how we might solve for either of those quantities? Alan, you got any thoughts? IL at 0 minus is equal to 3 amps. Okay, anybody got a problem with that? Pardon? It sure does. All of the current will flow through the through that 5,000 ohm resistor. And actually, I'm going to make this milliamps because I just realized that I'm using kilo ohms, and so stuff's going to get ridiculous in a second. But all of that 3 milliamps of current will flow through that 5 kilo ohm resistor. And then what path is it going to take? Yeah, because they're in series. And then it has a choice of flowing to the left through the 2 kilo ohm resistor or flowing straight down through the short circuit. It's going to choose the short circuit, right? So that's why IL Drew, I think you were going to tell me what VR is. Negative 15 volts. The current's entering the negative polarity terminal, so it'll look like negative 15 volts. So just to be clear here, that's negative 3 milliamps times 5 kilo ohms is equal to negative 15 volts. And all right. How do you guys feel about our circuit analysis at t is equal to 0 minus? Hopefully fairly straightforward. All right. Now we analyze the circuit at t is equal to 0 plus. All right, so at t is equal to 0 plus, that current source is closed or is connected to that terminal B, right? So what we're going to have is this guy. We have our 2 kilo ohm resistor connected in parallel with our inductor. And then we have our 5 kilo ohm resistor here. And then over here, we have our short circuit and our 3 milliamp source. Right? So we know that our inductor current IL at 0 plus has to be what? Three milliamps. Why? Say it loud and say it proud. Exactly right. It cannot change instantaneously. So the current flowing through the inductor will be at t is equal to 0 plus has to be what the current flowing through the inductor at t is equal to 0 minus was. I know that I've said that sentence a lot. I'm going to continue saying it a lot. So I'm going to treat this inductor as a 3 milliamp current source direction down. What is my voltage VR at 0 plus going to be? Why? Exactly right. So the voltage drop across our resistor here is going to be 0 volts. All right. I'm going to skip ahead to step 4. Yes. Okay, so let's look at what this switch is doing. Fantastic question. It's good for you guys to understand what's happening, right? So our switch is in, so this is our pivot point for our switch, right? And up here is position A, which is connected to that 5 kilo ohm resistor. This is how it was closed at t is equal to 0 minus. At t is equal to 0 plus, it pivots down and the current source is connected to just that short circuit. So we just see that that current of 3 milliamps flows around in that little bitty loop on the right-hand side, but that leg of the 5 kilo ohm resistor is left open circuited now. Does that make sense? Okay. So we are electing not to analyze the circuit at t is equal to infinity here because we know that the answers are just going to be 0 in this case. So I'm going to save us a little bit of time. So step 4. Determine LEQ and REQ during the transient condition. What's LEQ going to be? There's only one inductor, so it's just going to be 6 millihenries. Six millihenries, okay. And I'm going to meticulously draw what our circuit is going to look like to determine our resistance again, okay? So during the transient condition, we have our 2 kilo ohm resistor in parallel with our inductor. We have our 5 kilo ohm resistor, and then out over here, we have our short circuit connected to our 3 milliamp source. Since we are finding Thevenin equivalent resistance, we need to be looking at a dead network, which means I need to do what? Turn off my current source. I do that by open circuiting it. I'm finding the Thevenin equivalent resistance with respect to out, and I look in through the open circuit terminals where the inductor used to be. What do I see? Just 2 kilo ohms, right? So in this case, the 5 kilo ohm resistor got disconnected during the transient condition, so it no longer affects anything, right? So we just see the 2 kilo ohm resistor. So REQ is equal to 2 kilo ohms. So use step number 5, apply our generic equation. So what we'll have, gosh, I lost that there. Our generic equation, as a reminder, is that y as a function of time, where y can represent voltage or current flowing in our circuit, is y at 0 minus for t less than 0 minus, and y at 0 plus e to the minus r over lt for t greater than or equal to 0 plus. So how should our inductor current behave? What's its mathematical model going to be? What was it at t is equal to 0 minus? Pardon? 3 milliamps, all right. So we have 3 milliamps for t less than 0 minus. What was it like at t is equal to 0 plus? Jumping too far ahead. At 0 plus explicitly. Still 3 milliamps, right? Then we multiply it by e to the negative, and then we have r, which in this case is 2 kilo ohms, divided by 6 millihenries. So what's 2 kilo ohms over 6 millihenries? It's going to be 1/3 times 10 to the minus, or excuse me, 10 to the 6th, right? So 3.333 times 10 to the 5 t, right? So just to be clear here, this is 2 amps, because this is a current, my bad. T greater than or equal to 0. Okay. Yes, milliamps, thank you. Thank you very much for correcting me. All right. So I'm in a little bit of a conundrum here because I have not yet talked about how capacitors behave, and we don't have a whole heck of a lot of time. So I'm trying to decide whether or not to spend 10 minutes talking about capacitors, or if I want to give you guys the in-class assignment, which is all about inductors anyway for today. What are your thoughts? So I will tell you this, the homework assignment associated for today's lecture does have capacitors on it. So it might be useful to do that, but the amount of understanding, it'll just take us a couple of minutes really to go through it. I'm making an executive decision. We're going to talk about capacitors. All right, we're going to talk about capacitors, but we're not going to do an example problem because, as you're going to see, it's going to be practically identical. All right, so the first order RC circuit might look something like this. We have a voltage source, connected to a resistor. I'm sorry, what was that? Yes, sir. Connected to a capacitor. Like so. So we're just going to talk our way through what's going to happen with this guy instead of going so rigorously into it. All right. At t is equal to 0 minus, the capacitor has some voltage across it, right? What would it be? Exactly right. If the capacitor has a voltage drop across it, what does that mean? It's storing energy. When that switch opens up, what happens is the capacitor starts to discharge and give its energy to the resistor, which converts that electrical energy into heat. So it is effectively the exact same mechanism that's going on in the inductor. So it stands to reason that it should behave pretty dang similarly. All right. So I'm going to call this quantity right here VC of t, and I'm going to say that this current is IC of t, and this current is IR of t. And applying Kirchhoff's current law tells me that IR of t is equal, or excuse me, IR of t plus IC of t is equal to 0. I can express IR in terms of that capacitor voltage VC. So IR is just VC of t divided by R. And IC of t is C dVC of t by dt is equal to 0. And oh no, I've got a linear homogeneous first order differential equation again that we know how to solve by using an exponential function. So we guess that VC of t is going to be of the form A e to the st. If we substitute that in, we find that we have 1 over R A e to the st plus SC AE to the ST is equal to 0. And grouping terms, we have A multiplied by 1 over R plus SC E to the ST is equal to 0. And in this case, S must be what? Exactly right, -1 over RC. So we have AE to the negative T divided by RC. At T is equal to 0, we would have VC of 0 is equal to AE to the 0, which is equal to A. So our initial condition on this guy just needs to be VC of 0. That's how a capacitor behaves. It also exponentially discharges. Since the voltage drop across a capacitor is an exponential discharge. That means the voltage drop across the resistor is an exponential discharge, which means the current through the resistor is an exponential discharge, which means the current through the capacitor follows that same exponential decay. So again, if anything in the system has this exponential decay dependence, everything in the system has this exponential decay dependence. So what do you think the steps for analyzing this type of circuit would be? Step 1, analyze it at t is equal to 0 minus. Step 2, analyze it at t is equal to 0 plus. Step 3, analyze it at t is equal to infinity. Step 4 changes, because now we have to find CEQ, not LEQ. But other than that, it's literally identical. Step 5, plug crap into our generic equation. So it's the same exact process, except now the exponential decay is defined by the product of the resistance and the capacitance instead of the ratio of the resistance and the inductance. In every other way, these guys behave identical.